Right now, at this very moment, a telescope floating a million miles from Earth is doing something that sounds like science fiction. It's breaking starlight into rainbows, tiny precise rainbows, to sniff the air of worlds so distant that their light has been traveling toward us for decades. And what we're finding on some of these alien worlds? It's shockingly strange. Clouds made of minerals, skies filled with carbon dioxide, atmospheres that shouldn't exist. And just maybe, somewhere in all that data, hidden in the spectral lines and chemical signatures, we might be catching our first real glimpse of another living world. I'm talking about the James Webb Space Telescope, and today we're diving into one of its most ambitious missions, reading the atmospheres of exoplanets, planets orbiting distant stars, and searching for the chemical fingerprints that could indicate life itself. But before we get to alien air and biosignatures, let me ask you something. Have you ever wondered how we can possibly know what the atmosphere of a planet light years away is made of? How do we analyze air we can never touch on a world we can never visit? That's exactly what we're about to unpack. First, let's talk about the telescope itself. The James Webb Space Telescope isn't orbiting Earth like Hubble does. It's stationed at a point in space called Lagrange Point 2, L2 for short, which is about 1 million miles away from our planet, in the direction opposite the Sun. At this gravitational sweet spot, Webb can maintain a stable position relative to Earth while keeping its instruments incredibly cold, which is absolutely critical for infrared observations. And that's the key word, infrared. While Hubble primarily observes visible light, the light our eyes can see, Webb is optimized for infrared wavelengths. Think of infrared as heat radiation. Everything that's warm emits it. Why does this matter? Because infrared light allows us to see through cosmic dust clouds that would completely block visible light. It lets us detect the faint heat signatures of planets orbiting other stars. It allows us to peer back in time to the earliest galaxies whose light has been stretched into the infrared by the expansion of the universe itself. Webb's primary mirror is enormous, 6.5 meters across, composed of 18 hexagonal segments coated in gold. That gold coating is specifically chosen because gold is incredibly reflective to infrared light. Every design choice, every component, every system on this telescope was engineered for one purpose: to capture the faintest infrared photons from the most distant and ancient objects in the cosmos. And right now, one of the most exciting applications of that capability is the study of exoplanet atmospheres. We're literally analyzing alien air from millions of miles away. If that doesn't blow your mind, I don't know what will. Drop a comment and tell me, if you could analyze the atmosphere of any planet in our own solar system, which would you choose and why? So how exactly do we read an alien atmosphere? How do we determine what gases are present on a planet we can barely see as a dot of light? The answer lies in a technique called transit spectroscopy, and it's one of the most elegant methods in modern astronomy. Here's how it works. When an exoplanet passes directly in front of its star, an event called a transit, some of the star's light filters through the planet's atmosphere before reaching us. Not all wavelengths of light make it through equally. Different molecules in that atmosphere absorb specific wavelengths. Water vapor absorbs certain wavelengths. Carbon dioxide absorbs others. Methane has its own signature. Oxygen has its own fingerprint. By splitting that filtered starlight into a spectrum, essentially a detailed rainbow showing every wavelength, we can identify which wavelengths are missing or dimmed. Those dark lines in the spectrum? They're absorption lines, and they tell us exactly which molecules are present in that alien atmosphere. It's like reading a chemical barcode written in starlight. But there's a catch. The signal is incredibly faint. We're talking about a planet that might be 100 times smaller than its star. And the amount of light that actually passes through its atmosphere is a tiny fraction of the total starlight. Detecting these subtle changes requires extraordinary precision, and that's exactly what Webb was built to provide. This is spectroscopy at its finest. The same fundamental technique that scientists have used for over a century to understand the composition of stars now applied to the atmospheres of worlds beyond our solar system. We're essentially sniffing alien air from across the galaxy. Now, when we talk about analyzing these atmospheres, we're not just cataloging gases for the sake of it. We're searching for something specific, signs of habitability, signs that these worlds might support life. Many researchers frame this search around what's often called the 4 keys to life. These are the fundamental requirements that, as far as we understand biology, seem necessary for life as we know it to exist. Key number 1, liquid water. Life on Earth is utterly dependent on water as a solvent, a medium for chemical reactions, a transport mechanism for nutrients. Every living thing we've ever found requires it. Key number 2, essential chemical elements. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the building blocks of proteins, DNA, cell membranes. We need to find these elements present and accessible. Key number 3, an energy source. Life requires energy to maintain its complex structures and drive its metabolic processes. On Earth, that's primarily solar energy captured through photosynthesis, or chemical energy from geological processes in deep-sea hydrothermal vents. Key number 4, time. Life requires stable conditions over long periods to originate and evolve. A planet that's constantly being bombarded by radiation or whose surface is being regularly sterilized by catastrophic events is unlikely to develop or sustain a biosphere. When Webb analyzes an exoplanet atmosphere, scientists are looking for chemical signatures that might indicate these conditions are met. The presence of water vapor, carbon dioxide, and methane. Oxygen in quantities that suggest it's being constantly replenished, because oxygen is highly reactive and would quickly disappear from an atmosphere unless something, like photosynthetic life, is continuously producing it. But here's the crucial point, and I want to be absolutely clear about this. When scientists detect these molecules, they're not announcing, "We found aliens." They're saying, "We found conditions that might support life," or "We found chemical signatures that are consistent with biological processes." The distinction is critical. We're building a case, gathering evidence, narrowing down the possibilities. We're identifying worlds worthy of further study, targets for future, even more powerful telescopes. Before we continue, let me ask you this. Do you think we'll find definitive proof of extraterrestrial life in the next decade? In the next century? Or do you think we're alone? Leave your thoughts in the comments. I'm genuinely curious what you think. So what has Webb actually found so far? What if those first observations revealed about alien atmospheres? The results have been remarkable, even if they haven't included a definitive biosignature yet. One of Webb's first targets was a planet called WASP 96b, a gas giant located about 1,150 light-years away. It's what astronomers call a hot Jupiter, a massive planet orbiting extremely close to its star, with scorching temperatures and rapid orbital periods. Webb's observations revealed clear signatures of water vapor in its atmosphere, along with evidence of clouds and haze. The level of detail was unprecedented. Scientists could determine not just that water was present, but how much and at what altitudes. Another early target was WASP 39b, another hot Jupiter about 700 light-years away. Webb detected carbon dioxide in its atmosphere, the first definitive detection of CO2 on an exoplanet. The data also revealed evidence of clouds made not of water ice or droplets like on Earth, but of minerals, silicate particles forming in the scorching upper atmosphere. Think about that for a second. Mineral clouds, skies where it might rain molten glass. These are worlds utterly unlike anything in our solar system. Extreme environments that challenge our understanding of planetary physics. But here's the thing. There's a reason Webb is starting with these hot Jupiters. They're easier to study. They're big, which means more light passes through their atmospheres during transits. They're hot, which means they emit more infrared radiation that Webb can detect, and they orbit close to their stars, so transits happen frequently, sometimes every few days, giving us multiple opportunities to observe them. These planets are our training ground, our proof of concept. We're perfecting the techniques, calibrating the instruments, learning to separate atmospheric signals from stellar noise and systematic errors. But they're not the end game. The real dream targets are much smaller, much cooler, and much more challenging to observe. Rocky planets orbiting in the habitable zones of their stars, the region where temperatures allow liquid water to exist on the surface. Planets roughly Earth-sized, with atmospheres potentially similar to ours. These are the worlds where we might detect biosignatures, chemical combinations that are difficult or impossible to explain without invoking biological processes. The classic example is the simultaneous presence of oxygen and methane in large quantities. On Earth, oxygen makes up about 21% of our atmosphere, constantly produced by photosynthetic organisms. Methane is produced by various sources, including bacteria in anaerobic environments. Critically, oxygen and methane react with each other. They don't coexist in chemical equilibrium. The fact that both persist in Earth's atmosphere is a direct result of biology constantly replenishing them. If Webb were to detect a similar chemical disequilibrium on an exoplanet, substantial oxygen and methane together, or other combinations of gases that shouldn't coexist, it would be compelling evidence for active biological processes. But there's a problem. Actually, several problems. First, the signals from small rocky planets are incredibly faint. Earth-sized planets have thin atmospheres compared to gas giants. The amount of starlight that filters through during a transit is minuscule, making spectroscopic analysis extraordinarily challenging. Second, stellar activity complicates everything. Stars aren't perfect, stable light sources. They have spots, flares, and atmospheric variations of their own. These can create false signals or mask the true atmospheric composition of the planet. Separating the planet's signal from the star's noise requires sophisticated analysis and often repeated observations. Third, telescope time is precious and competitive. Webb is one of the most in-demand scientific instruments ever built. Thousands of astronomers worldwide are competing for observing time. Studying a single Earth-like exoplanet's atmosphere might require dozens of transits, consuming hundreds of hours of telescope time. The decisions about which targets to observe and for how long are agonizing. Webb is currently observing several promising candidates in the TRAPPIST-1 system, 7 Earth-sized planets orbiting a small, cool star about 40 light-years away. Some of these planets orbit in the habitable zone. Early observations have revealed that at least some lack thick hydrogen atmospheres, which is actually good news. It means they might have denser, more Earth-like atmospheres worth studying in detail. But we're still in the early stages. Each observation refines our understanding, but also reveals new complexities and challenges. And this brings us to the biggest question of all. How close are we to finding life? So let me be direct with you. How close are we really to finding life beyond Earth? When will we get that headline? That definitive announcement that changes everything? The honest answer is we don't know. It could be next year. It could be decades from now. It could be centuries. What we're doing right now, what Webb is doing, is building the foundation. We're developing the tools, refining the techniques, cataloging the targets. We're learning which types of planets are worth studying, which stars are quiet enough to allow clear atmospheric observations, which chemical signatures are genuinely indicative of biology versus geological or atmospheric chemistry. There's a real possibility that Webb could detect a genuine biosignature during its operational lifetime. The telescope is designed to function for at least 10 years, potentially longer if fuel reserves hold out. Every year, we're improving our analytical methods, our understanding of exoplanet atmospheres, our ability to model complex atmospheric chemistry. But there's also a real possibility that Webb won't have the sensitivity to definitively detect life on an Earth-like planet. That confirmation might require the next generation of space telescopes, missions currently in the planning stages, like the Habitable Worlds Observatory, designed specifically to image and characterize Earth-like exoplanets. And you know what? That's okay. That's how science works. Each generation builds on the work of the previous one. Webb is revolutionizing our understanding of exoplanets, but it might be laying the groundwork for a future mission that gets the final answer. There's something profound about that. We're part of a multi-generational quest, a scientific endeavor that spans not just years, but potentially decades or centuries. The work we're doing now, the data Webb is collecting, will inform missions that haven't even been designed yet. Here's what I want you to take away from this. When, not if, but when, we finally detect an atmosphere on a distant planet that genuinely screens life, when we see those chemical signatures that can only be explained by biological processes, when we realize that we are definitively not alone in this universe, you and I will remember these early images. The deep fields full of anonymous galaxies, the first spectra showing water vapor on hot Jupiters, the painstaking analysis of rocky planets orbiting red dwarf stars. We'll remember that it all started here, with a telescope a million miles from Earth, breaking starlight into rainbows, sniffing alien air, searching for worlds where life might call home. And maybe, just maybe, we're closer than we think. If this video expanded your understanding of how we're searching for life beyond Earth, please hit that like button and subscribe to this channel. We're exploring the biggest questions in space science, and I don't want you to miss what's coming next. Share this with someone who needs their mind blown today. And let me know in the comments, what do you think the first confirmed biosignature will be? What molecule or combination of gases will finally prove we're not alone? Thank you for watching. Keep looking up. The universe is waiting.